Hello, everybody. This is Professor Ma, and this is the second part of the volume of solids of revolutions. From briefly from the past, we have these formulations of what is area, and the area is the sum of cross-sectional length times little width, and that sum turns into growth. Then we have the second, which is the extensions into the volume. What is volume? Volume is the cross-sectional area times little thickness, dx, and that is the volumes of a very thin disk. And then we add up all these thin disks, and that turns into integral of that's integral. That's a volume. Okay, and now we're going to look at this particular formula for the volume, saying that actually there are other ways to do this volume. That is, I don't have to look at these solids, which over here is like these, almost like that, let's say, okay? I don't have to look at these solids as slicing into slabs of salami. I can slice it different ways. I can obtain these small bits of volume in different ways. And how so? This is what we're going to do. We're going to actually imagine these things actually stacks up like a bunch of disks that one loops inside the others, like Russian dolls. Okay, and so they are formed from these cylinders, and so this is second method, the cylindrical methods, and the well, let's go through this first. Okay, and so let me switch new here to okay, cylindrical methods. Okay. Let me just jump to slide number 18, 19. Okay. If you read this PowerPoint, slide number 1 through 18, we're going to do it in our next section again. So if you want to delay that, it's fine. I'm going to jump into the second part of the presentations. Okay. One thing is very important about rotations. We're going to rotate templates to make solids of revolutions, right? And if we follow, as the template rotates around on axis be like this. If we follow a line, a cross-sectional line in the template that's parallel to the axis, like this red line over here, that as we follow it rotates around this rotational axis, and in space it will form a cylinder. Okay, and let me point out something. What we are going to do in examples is that because the rotations of the line around the axis as it rotates, it has to be parallel to the axis that it rotates around. So if the axis point this way, then the rotation of the line, it has to be parallel to it. You have to follow, in other words, you have to follow horizontal line. If the rotation axis is horizontal, if the rotation axis is vertical, you have to follow vertical line to make those cylinders. And we're going to track those cylinders. Okay, so and let's assume that we're going to rotate vertically around orbit around the vertical axis. Okay, that means it forms these cylinders, and this cylinders and has a delta x thickness because the line itself, let's say, is delta x thick distance. And then if I slice open this cylinder, it is almost a rectangular sheet with delta X thickness. It has a little extra, okay? The rectangular volume of a rectangular sheet that's very thin, delta X thickness. The volume of this is easy to track. This is the 2 pi r times h, the height, which gives the volume times the delta x. Okay, that's the volume of this rectangular box, if you like, very thin rectangular box, and that's approximately equal to the volume of this can, if you like, cylinder, very thin cylinders. Except there's a little parts extra we didn't count, but in the approximations that can be ignored. That will go to zero. We get the Cassius cylinder very, very thin. So good. And so now suppose I want to follow this particular template here from A to B, okay, a plate that's rotating vertically. I'm going to follow a vertical line in there, and I'm going to write down the formula of the cylinders that it generates, the area of the cylinders. Okay, and what do I have to track? Well, there are two things. As it generates a cylinder, as it rotates, and the formula require we track the distance, the radius of the rotations. In other words, the distance from x, whatever the point x is, to the rotational axle. Okay, so at this point you have to clearly understand which directions is the axis. It's to the left or to the right, because the distance has to be the right hand point subtract the left hand point. Okay, so at this point you have to think of who's on the right, who's on the left, in order to extract this distance. Okay, and now of course, what's the height? The height is just the function f of x. Okay, and then you have the thickness delta x. So as it goes around, and then the area of this, sorry, the volume of this very thin shell is this is the area of the surface area times the thickness of that very thin shell, the surface. And so then this is dV, if you like. This is what we call dV. That is the one of these. Now, of course, in the volume of this is going to be the sum of this dV. Then, by fundamental theorem of calculus, is that sum turns into integral. Okay, adding this little volume turns into just this distance x fx dx. Okay, this is the cylindrical formula. So the rest is so volume V is equal to 2 pi times the radius times the height is f of x, dx the thickness. Okay, that's a dV, and I'm adding this dV. Then the fundamental theorem of calculus said, oh no, the easy, the pass it to limits. Dx go to 0, then it becomes a definite integral. Because it's a shell method. Okay, and what about the shell method? Actually, for a you can kind of well, if you think about the reason we talk about this particular method is that in other words, if you can extract, if I give you a solid, it kind of in certain shape, in a certain regularity. If you have by hook or crook, if you can slice, if you can somehow cut these solids into little thin slices, it doesn't matter how to be straight, a curve, in space, being a regular fashion that you can keep track of. Okay, and each one, the size of each one of these thin shells, then you can integrate it in that fashion that you give the following. Like you just add up all these very thin slices, like Pringles. Okay, if you can figure out the surface area of Pringle, then you stack a bunch of Pringles together, then you can figure out, add them up. You can integrate the volume using that surface, stacking up those surfaces. Okay. And here's our two examples. And one example is vertical, and so we're going to track vertical distance. Okay, so we're tracking, what do we have to track? We have to track a line that's parallel to the spinning axles. So in other words, you do track a line like this, and as it spin, and this is going to be the distance, going to be the radius, and this is going to be the height of the cylinder. And that's basically the formula you have to extract. You have to say, oh, what is the radius expense? Okay, and the height is top minus the bottom. The top one minus the bottom one. Okay, what's the distance to the spinning axle? Right hand side, x equal to 3. So anything where there's the x, subtract the left hand side x, 3 minus x. Okay. So dx is 3 minus x. And therefore, the volume is going to be integral of 2 pi d times that times dx. Integrate that. Now, let's do these. Now, what happens if I spin these things around the horizontal axis? Now, I need to track horizontal line to form that cylinders. Okay. Now, I need to extract x coordinate in terms of y. Okay, this go from y from 1 to 0 to 1. Okay. So first I convert all the equations in terms of what's in the x coordinate. Okay. And the template is very important. Now everything is horizontally tracked, so the y will go from 0 all the way up to 4. Okay. So I'll leave it up to you solve for that point. Okay. So now we have these situations. Okay. And now I'm following the cylinder as it forms, as it rotates around. And now the radius is from here to here. Okay. Top minus the bottom. Okay. So you got y plus what? So let's do the cross-sectional length first. The right minus the left. Given y. Okay. Given y is the right hand side is x to the root y. The left hand side is y minus 2. So you subtract right minus left. Now, what's the rotational radius? The top minus the bottom. What's the top? The top is y. Given the y, okay, given the y here. Well, where's the bottom one? Minus 1. So y minus 1. The distance is y plus 1, right? Here's y, and there's one more, so y plus 1. Okay, so that's the integral. Okay. And that's it. That's the cylindrical method. You have to just keep track whether you're rotating a vertical line around vertical axis, so you get vertical distances versus the radius this way. And then you are doing this way, then you have to track the horizontal distance, and then this vertical for the radius. Yeah, that's it. Okay. Okay. Until next time. Bye bye.